All right, I have one more set of notes around topic 1.3a that has to do with relative velocity. And so let's take a look at this. We have a learning intention, that is to determine the relative or the observed velocity between two objects whose velocities are known relative to the ground, let's say. So we need to be able to determine the relative velocity between two objects. All right. In order to get started, I want to talk about maybe you've had this experience of just flying on an airplane before. So let's just picture an airplane. It's kind of going through some kind of a flight. It's moving along at a pretty good clip, and you are on the airplane sitting next to someone. So this is you. This is the person that you're sitting next to. And let's say the airplane is going some, maybe 600 miles an hour, like 270 meters per second, that is about. It's flying fast, 270 meters per second in some direction. But when you look at the person next to you, even though they are going 270 meters per second, it seems like they are stopped. And so there's this idea in physics where velocities are meaningless unless you give a point of reference. That is to say that, our Earth is whirling at tens of thousands of miles an hour around this really close star that we call a sun. And our sun and our entire solar system is whirling at hundreds of thousands of miles an hour around the center of our galaxy that we call the Milky Way. And even our own galaxy, the Milky Way, is moving at millions of miles per hour towards a region of space that we call the Great Attractor, that we don't really understand. It's some combination of dark matter and matter, but it's got a lot of mass to it, and we are really moving quickly towards it. No worries, not in your lifetime, at least. So we are going to be talking about this idea of velocity relative. So your velocity relative to that person, or an observed velocity. And let's zoom into our airplane here for a second. And let's say here's you're sitting in your chair on the airplane. I'm not very good at drawing, so this is you sitting on your chair, and that's your little flotation device in case you hit the ocean. They tell you that to make you feel better. This is you sitting on your chair inside the airplane, and walking past you is somebody. All right, they're walking past you at some, it appears to you that they're walking past you at about 1 meter per second. But to look at this situation, you would have to say that your velocity, v of u, is about 270 meters per second, we said. And in order for them to look like they're walking past you in the aisle, going past about 1 meter per second, their velocity, v of them, has to equal maybe 271 meters per second in that same direction, headed there. So it appears to you, because they're going 1 meter per second faster, that they are moving 1 meter per second down the aisle. And it looks like they're moving slow to you, but the fact is that both of you are moving quite quickly compared to anybody on the ground. All right. So relative velocity really refers to, let's write this down, this is good. Relative, you should be writing this down. These are good notes. Relative velocity refers to the difference between the velocity of an object, the thing you're looking at, and the velocity of the observer. right, so this is kind of an important idea. This idea that if I was to write v, the velocity of A relative to B. All right, let's write what that means. That means the velocity of A relative to B. All right? The velocity of object A relative to the observer that we'll call B is equal to the difference between the velocities of the objects. That is to say, it's equal to the velocity of A relative to the ground or whatever, just the straight velocity of A. Take out the velocity of the observer, right? The difference means we're going to subtract the velocity of our observer. So we have this equation that says that the velocity of A relative to B is just the velocity of A minus the velocity of B, the observer. And let's talk about how that might be used. In our airplane, do you see that, I'll jump back here. In our airplane, do you see that if I was to say that this person is person A and you are person B, the observer, that the velocity of person A relative to you, the velocity that it appears that they're moving, is just this. It's this idea of the velocity of A relative to B is equal to the velocity of A minus the velocity of B. The velocity of A we said was 271 meters per second minus the velocity of B, which is your velocity, 270 meters per second. And when we subtract these two, we get 1 meter per second. This idea that it appears that they're going 1 meter per second because you're both traveling very quickly together for the 270 meters per second. All right. Well, that one-dimensional stuff where everything's moving in a straight line is not IB physics. And truthfully, we know that velocities are vector quantities. So they have a magnitude and a direction. I want to take a look at another problem. All right, so let's do boats. Let's say we have two sailboats. And another bad drawing here. This is sailboat A. We'll put it on the little sail there. Sailboat A, and this one here, let's say it looks something like this. This we will make sailboat B. All right, and both of these sailboats are moving along across the water. All right. Well, if we were to say that sailboat A is traveling at 15 meters per second and sailboat B is traveling at 10 meters per second, then if you were inside sailboat A, I should make this vector a little longer. If you were inside sailboat A, it would look like you were moving towards sailboat B, which would have the appearance that sailboat B was moving towards you, right? So if you said, what is sailboat B doing? You would say, they look to be moving towards us at 5 meters per second. And sailboat B would have the same idea. It would say, well, they look to be moving towards us at 5 meters per second. But what if, rather than all in a straight line, what if our boats were traveling, let's look from above, right? What if our boats were traveling in this way? Here's sailboat A from above, here's the sail. All right. And this is A, and let's say B is headed down this way. So here's my sail for B. This is sailboat B, and sailboat B is jetting this way, and sailboat A is jetting this way. And we'll put up some directions here that might be useful. So I'll call this direction like on a map. So no longer are we looking from the side like this. Now we're going to look straight from above, and I'm going to say that this direction is north and this direction is east, and that sailboat A is headed east and sailboat B is headed south. Well, then what if I was to ask, what is the velocity of sailboat B relative to sailboat A? And that is to say that what if you were placed here? This is you, right? What if you were placed here on A? Which direction would it look like sailboat B was going? And let's do the math on this. All right, so here's our problem. And let's take a look at how we might be able to go about solving it. All right. Well, we know that this is true, that the velocity of B relative to A is equal to the velocity of B minus the velocity of A. And for vector quantities, that's saying this. That's saying that the velocity of B with respect to A is, we don't subtract vectors really. What we do is we say minus is really the same thing as adding a negative. So what would that look like? What does it look like to say velocity B, that's this guy here, BB, plus a negative VA? All right, well, in order to add vectors, we're gonna do this. We're gonna draw out an origin, and we're gonna say here from our origin, velocity B, VB, looks like this. So we have VB here plus a negative VA. So if VA is going to the right, negative VA, I would have to add to this. This is what negative VA looks like. And our resultant vector then is a vector that is headed, well, what direction is this? Well, let's look back at our, at our map compass here. We have north is up and east is to the right. So this vector that's headed down this way, if this is the velocity of B relative to A, it looks like it's headed southwest. So if you are in boat A, it looks to you like boat B is going southwest. And maybe it makes sense why that is. Because if you just take a look at your velocity, ignore this one for a second, the fact that you are going east makes boat B look like it's coming towards you, going west. So boat B is going to look like it's going west because of this velocity. And then if we look at this situation, just this velocity, the fact that they're going south, well, to you it looks like they're going south, right? So your velocity makes them look like they're going west, their velocity makes them look like they're going south, and the combination of the two playing at the same time makes them look like they're going southwest. All right, let's take another example of this with some numbers. And here's what this looks like. All right, so we'll stick with sailboats here. We'll say, here's our example. All right, our example is this. You are in a sailboat headed east at, let's say, 3 meters per second. Lisa is in a different sailboat. Headed north at 4 meters per second. Okay. And the problem is going to ask that you determine Lisa's velocity relative to your own or your boat. Right? You and your boat are traveling at the same. So, in looking at this problem, we'll say, so the velocity of AB is equal to the velocity of A minus the velocity of B. And in this problem, we say, well, this is the velocity of our object that we're looking at, and that is Lisa. And this is the velocity of our observer, and that is you. Right? So this is, what is Lisa's velocity? Take away your own. All right. Well, let's jump in here. In order to solve this, we're going to say we need the velocity of Lisa plus the negative velocity of you. All right, and let's draw a vector diagram that shows that situation. We have the velocity of Lisa. All right, let's set up, we'll say this is east and this is north. All right, the velocity of Lisa is north at 4 meters per second. So if we have some kind of an origin here, Lisa's velocity is north at 4 meters per second. V sub Lisa equals 4 meters per second north. All right, and your velocity is east at 3 meters per second, right? But we want to add not your velocity, we want to add negative your velocity. So rather than 3 meters per second east, we're going to add 3 meters per second the other way, west. And this is V, your velocity, which is 3 meters per second. Right. The resultant velocity is going to be directed this way, right? So this is the resultant. This is going to be the velocity of A relative to B, or the velocity of Lisa relative to you. All right. And how do we determine the size of that? Well, this is a right triangle, right? This is your one's going north and the other is west. So that's a 90-degree angle. We have a right triangle, and we can solve that. We know this is the hypotenuse by saying that, let's switch colors here, that C is equal to the square root of A squared plus B squared. And in this problem, we have, let's call, this A and this B, right? So we have, this is equal to the square root of 3 squared plus 4 squared. And that's 9 plus 16, that's the root of 25. So C is equal to 5 meters per second, whatever the units are on these. The units on this will be the same. So your velocity, Lisa's velocity relative to you is 5 meters per second. Now we just need the direction. And that's a tricky problem, but we can do this, all right? So we found the magnitude of the vector, 5 meters per second. We need now the direction of the, and in order to do that, we have to use some trig functions. So let's take a look at our triangle first of all, and let's say we're gonna find this angle here. Let's call that angle theta, and we're gonna figure out what that is. And the way we find this angle is we're gonna use SOHCAHTOA, just a part of SOHCAHTOA. We're gonna use the TOA part, right? So TOA means that the tangent of theta is equal to the opposite divided by the adjacent. And in our problem, the tangent of theta will equal the opposite, which is 3, divided by the adjacent side, which is 4. So the tangent of theta in our problem is equal to 3 over 4. And in order to solve this, we have to get theta by itself. We want to do the opposite of whatever tangent is, and that happens to be tangent to the negative 1 power of this side, and we're going to do the same thing over here, tangent to the negative 1 power of this side. Here we have tangent, negative 1, inverse tangent and tangent cancel out. We're left with theta is equal to whatever the inverse tangent of 3 over 4. Make sure your calculator is in degrees. The inverse tangent of 3/4 is about 37 degrees. So now we can say that Lisa's velocity relative to your boat is 5 meters per second at 37 degrees, and then this direction here, you know, it's not, we're not going north, we're not going straight north, we're going some amount towards the west of north, right? I mean, we would say that you know, if this is north, here's east and west, right? We are headed not directly straight north, we are headed some amount west of north. Yes? Just like, this is an important distinction, but I'm going to write down, this is 37 degrees west of north. Let's talk about that. That means to say west of north is really this. If we were 0 degrees west of north, well, that would just be north, right? Right? So 0 degrees west of north would just be straight north. And if I was to say that I'm 2 miles, so 2 miles north of Mayfair. Well, if I was to say I'm 2 miles north of Mayfair Mall, then you would know that you would start at Mayfair Mall and you would then go 2 miles north of there, and that's where I would find, you know, that's where you'd find me, Mr. Putnam. Well, this idea of saying 37 degrees west of north, you need to understand for your evidence, and this is what it's saying. It's saying if I'm 2 miles north of Mayfair Mall, then you start here, right? That means that we're going to start here at north, and we're going to go 37 degrees west of it, right? So we start directed right up at north, and if we go 37 degrees west of that, right? That direction there, if this is 37 degrees, is 37 degrees west of north. All right, so you have a little bit of practice to do, and then we're going to look at testing what you know about vectors. All right.